Now, let's pick some values. Let's say -2, -1, 0, 1, and 2 in both. -2, -1, 0, 1, and 2. In the first function, please, let's plug in -2. What do we get when we plug in -2? Careful. 2 raised to -2. Very good, excellent. 2 raised to -1. Perfect. So a raised to -n is 1 over a to the n. So 2 to -2 is 1 over 2 squared, which is 1/4. No, because I have to identify what it is, because I have to plot these ordered pairs. When x is 0, how much is y?
1.
Perfect. When x is 1, how much is y? Perfect. When x is 2, how much is y? Good. Now let's see what happens here at the end points. Ready? I'm going this way. 1/4, 1/2, 1, 2, 4, 8, 16, 32, 64, 128. Where am I going? Positive. Yes, which means positive. What do we call it? Very good. Of course. Of course. So now I'm going this way. Careful. Let's think. 1. 1 over 2. 1 over 4. 1 over 8. 1 over 16. 1 over 32. 1 over 64. 1 over 128. 1 over a million. Say it again.
Would it be 1 over infinity?
Correct. 1 over infinity. I have $1 and I want to cut a little piece, and I'm going to get to everybody, and whatever you're going to get. Let's say I start with China and India. They're the biggest countries. And I finally get to you. How much will you get? What is left? 0. Absolutely 0. Good. So let's graph what we have now, and then we look at the other one. So let's graph. Here's the graph. Please tell me the first ordered pair that I should plot. First ordered pair is?
-2.
Excellent. -2, 1/4. I'm going to say this. Second ordered pair, please.
-1.
Good. Third ordered pair, please.
0.
Excellent. Next ordered pair.
1, 2.
Next ordered pair.
2.
Good. Here it is. Two raised to x. The graphing calculator. Let's punch in y equals. Clear if you have anything in there. 2 power. I like to put parentheses. That's me. And now I want to graph using the standard viewing window. Of course, this is not the case. Please do not copy from the graphing calculator. The graph does not touch the x-axis. It does not go below the x-axis. Okay? So this is the graph of 2 to the x.
What does it do it then?
Say it again.
What does it do it then?
No, it gets closer and closer. So close from approaching 0, very close to 0,
Yeah, I'm just saying.
it goes up.
What does it do it there then? What does it show up? Is it because it was without?
Don't read, don't Don't always believe what the calculator gives you. Very good. Let's look at the other shape. So when x is negative 2, when x is negative 2, remember it's a fraction and the power is negative 2. So what do we get? So 1 over 2 raised to negative 2 is 2 raised to the second power, which is 4. So 4. When x is negative 1, very good. When x is 0, a number raised to 0, 1. When x is 1, good. When x is 2, good. Let's see where we're going this way and where we're going this way. 1, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 128. Where am I going? Very good, to 0. And what about this way? That's it. So let's graph this function. Can anyone identify the first ordered pair that needs to be plotted?
Negative 2, 4.
Negative 2, 4. Second ordered pair.
Negative 1, 2.
Third.
0, 1.
Fourth, please.
1 and 1/2.
And so on and so forth. This is the graph of 1/2 to the x.
It's the inverse. Not the inverse.
It's not the inverse. But I know what you mean. You mean not the inverse function, but you mean reversed in the sense that it's not increasing on all its domain, but it's decreasing on all its domain. Good. Can anyone give us the range of these exponential functions? Let's look at the graph.
Oh, it's
And also you can look at the chart. The chart will always tell you what the range is. Correct. Correct. 0 to infinity. This is a function that is increasing, and this is a function that is decreasing on all its domain. Can anyone tell us whether these functions are one-to-one?
Yeah.
By the,
horizontal line.
they are one-to-one. Okay, let's graph their inverses. We don't even know what the inverses is, the inverse function is, but we are ready to, we can graph it. What do I have to draw first when I graph the inverse of a one-to-one function? Exactly. Can anyone give us few ordered pairs for the first inverse function so I can graph it? Here's the chart.
They're just flipped, right?
Please. Yes.
1/4.
Very good. 1/4, negative 2.
Then 1/4. I mean 1/2.
Excellent. Then
0, 1.
careful.
No, 1, 0.
Perfect.
2,
Then.
1.
Very good. That's good enough. Please look at this. Are they symmetric with respect to y equals x? So this is the F inverse. For the other one, can anyone give us few ordered pairs so I can plot it? Plot them and graph the inverse function?
2, negative 4.
Careful.
4, negative
4, negative 2.
Very good. Excellent.
do -1.
Excellent.
1, 0.
Very good. Now, what happens to this point? Right? If the point is on y equals x, then if you reverse it, see y and x are the same here. All points on this line are the same. If you reverse it, if you reverse 1, 1, what will you get? 1, 1, right? So here it is. This is F inverse. Any questions? Okay, I would like to look at a couple of equations in a word problem and then we'll stop. Page 736, problem 21. 3 to x equals 27. This is what type of equation? It's not quadratic, it's not linear, it's not absolute value. It's exponential, thank you. Why? Because the variable in this equation is the exponent. Very good. It's an exponential. The left-hand side has base 3. Can I, by any chance, can I replace or present the right-hand side with the same base?
Yes.
How?
You would have 3 to 3.
Very good. So now we are not simplifying or dividing by 3. So please pay attention for 1 second. Two numbers are equal and they have the same base. What has to happen to their exponents? One more time. Two numbers are equal and they have the same base. What has to happen to their exponents for them to be equal indeed?
That's the same.
Good. So from here the conclusion is that x equals
3.
That's it. And no, not all exponential equations are this easy. For example, I'm looking at 27. 1/4 equals 2 raised to 3x. 736. 736. I cannot draw a conclusion till I present both sides with the same base. The right-hand side I cannot further simplify, it must stay like this. But is there any way I can rewrite 1/4 with the same base I have on the right-hand side? Is there any way of rewriting 1/4 with the same base, which is 2? Very good. So now I'm back to the previous situation. Two numbers are equal and they have the same base. What has to happen to their exponents?
It's the same.
Yes. So then -2 must equal 3x, therefore x must equal. Excellent. Okay, one more and then we'll look at a word problem. Like 35. Any questions? Stop me if you have questions, please. All word problems here are very easy. Very easy. 35. 81 raised to x minus 1 equals 27 raised to 2x. Now you can say, oops, this is slightly more difficult and I will have to agree. Can we present 81 and 27 using the same base? Perfect. How will I replace, or what do I write for the left-hand side? 3 raised to the... It's 9 times 9. It's 81. So how many 3's are in there?
6.
In 9 times 9.
That's
It shows
fine.
9 is 3. No, 9 times 3 to 9. How many 3s are in
Yeah, in 9 times 9. There are two in the first 9 and there are 2 more in the second 9. So how many 3s are in 81? Good. To x minus 1. So how many 3s as factors, of course, are in 27? We just looked at that.
3?
Good. So then is 3 to the third raised to the,
2x.
good. I have one more step. The left-hand side, I copy the base and I have to remember what to do with the exponents. So I copy the base and the exponents will be what do we do with 4 and x minus 1?
4x minus 1?
In parentheses if you want to say that. You have to multiply them, correct? So then I copy the base and then
3 parentheses.
but this is just here I had to use parentheses because I had x minus 1, but here it's just a 6x. So now the same, I'm back to the same idea. Two numbers are equal and they have the same base. What has to happen to their exponents? Please dictate and I will write it in.
It should be the same.
Correct. So then 4,
X minus 4
perfect,
equals 6x.
excellent. So whatever you want to do, so then I have negative 2x equals 4, so x must be negative 2. Let's read one word problem and then we'll stop. Yes, 41 on page 736. 41. The equation y equals 140,242 multiplied by 1.083 raised to x models the number of American college students who studied abroad each year from 2000 through 2009. In the equation, y is the number of American students studying abroad, and x represents the number of years after 2000. So y, number of students studying abroad, and x is 0 for the year 2000. Estimate the number of American students studying abroad in 2004. First of all, what type of function is this?
No. That's exponential.
Very good. Well, that's what we are talking about, correct?
So are you just replacing x with 4?
Exactly.
In this? That's awesome.
Exactly. So y equals 140,242 multiplied by 1.083 raised to the 4th power. So let's do this with a calculator. So 140,242 multiplied by 1.083 raised to the power 4. So roughly 100 and it says round answers to the nearest tenth of a billion dollars. Oh, I'm sorry. It is round the answers to the nearest whole. Okay, of course. Yes. So 192,927. 192,927 students studied abroad in 2004. Part B, last one. Assuming this equation continues to be valid in the future, use this equation to predict the number of American students studying abroad in 2015. What do I have to do to answer part B?
We just substitute x for 15.
So x equals 15 years.
And then solve.
So all I have to do is just plug it in. So go back and change 4 into 15. And it appears to be 463,772. As I said, all the problems here are very easy. So on Thursday,